You've probably handled a battery hundreds of times, but have you ever stopped to ask, how does this little cylinder power things? In this lecture, using the basic laws of charge, we'll build a battery step by step, and uncover not just why it makes electrons move, but also how it keeps them flowing at a constant rate, which is something we call an electric current. By the end, you'll understand exactly how a battery works, and what current really is, which is the key to making sense of any electrical circuit. Let's start by briefly recapping the electric potential. In this system of 2-point charges, a positive test charge moves from the positive potential region to the negative, while a negative test charge does the opposite. Instead of using this imaginary test charge, let's put a long thin wire here made of a conducting material, such as copper. Most wires in devices are made of copper, by the way. In a conducting copper wire, there are electrons, protons, and neutrons. As we discussed in Lecture 1, the protons and neutrons make up nuclei, while electrons are free to move around. Now, even in a thin metal wire, there are around 10 to the 23 electrons, so I'll use blue shading to indicate regions with more negative charges. In this example with 2-point charges, or charged spheres, there is a positive potential at one end of our wire and a negative potential at the other end. Therefore, there is a potential difference across our wire. You can probably make a good guess of how the electrons in our wire are going to react to this. Of course, they are going to move towards the positive end and away from the negative end to some extent. Now, to be accurate, as electrons are all negatively charged, they repel each other, so they can't all just bunch up at one end. They are also attracted to the positive nuclei in the wire. So overall, they move so that they balance all these electrical interactions. Don't worry too much about how all this would be practically calculated. The only point that's important here is that electrons in a conductor move when we apply a potential difference. Electrons drift in the opposite direction to the electric field. The potential lines I've drawn here are technically inaccurate for each individual electron, as each electron is also experiencing forces from all the nuclei and all the other electrons. But don't worry too much about this. We should also make it clear that the positively charged nuclei stay completely fixed during all this. The more positively charged part of the wire is simply caused by a lack of electrons here, rather than nuclei moving to the side. Now, this scenario is obviously not very useful to us. Yes, we've moved the charges in the wire a bit, but now they are stuck in place. However, imagine if there was a way that we could get the electrons in the wire to continuously move around a loop. Imagine we could replace these charged spheres with some sort of device where electrons could go in one way and come out of the other. This might seem ridiculous, as it would mean that a negative charge can move from a positive potential to a negative potential, which makes no sense based on what we've discussed over the last few lectures. But, believe it or not, this is possible using a very clever trick. It can be done using a device known as an electrochemical cell, or cell for short. You might be more familiar with the battery, which is just several cells attached together in series, but we'll get to that. Let's start by imagining two solid conducting materials. Now, we're going to discuss a light bit of chemistry here, but don't worry if you aren't familiar, as we can understand everything using the physics we've already discussed. First, let's return to the atom, which we introduced in Lecture 1. As we said before, the atom is charge neutral by default, as it has an equal amount of protons and electrons. Now, though an atom has a fixed amount of protons, electrons can be added or removed in some situations. When this is the case, the atom becomes an ion, which will be positively charged if an electron is removed, and negatively charged if an electron is added. Now, it turns out that certain atoms hold electrons more tightly than others. In zinc, electrons are less tightly bound, so they're at a higher potential energy and can leave the metal more easily. In copper, electrons are more tightly bound, so the copper sits at a lower potential energy. This difference in potential means there is an electric field, so electrons are driven from zinc to copper. Now, the deeper reason for this is a lot of advanced quantum mechanics, so we won't discuss it here. But the key result is that the electrical potential energy of an electron in zinc is higher than if it was moved to copper. So, if we were to connect the zinc and the copper with, say, a copper wire, electrons would start moving from the zinc to the copper. However, this would be very short-lived, because as electrons start moving, the copper is quickly becoming more negatively charged, while the zinc is becoming more positively charged. So, electrons in the zinc are now more attracted to the zinc and less attracted to the copper than they were before. So, the potential energy of an electron in the zinc quickly equalizes to the potential energy it would have in the copper. So, the potential gradient, i.e. the electric field, quickly drops to zero. So this won't work on its own. We need some way of keeping both the zinc and the copper neutrally charged. By the way, in this system, the zinc and the copper rods are also known as electrodes, which are just conductors where electrons can enter and leave. The zinc is known as the anode, which is an electrode that gives up electrons, while the copper is known as a cathode, which takes in electrons. The electrochemical cell is made complete by introducing an electrolyte. An electrolyte is just a liquid or solid containing lots of positively and negatively charged ions. We connect this electrolyte to the anode and cathode. Now, when electrons start moving and the anode and cathode become charged, the positive and negative ions in the electrolyte move to cancel this out. This happens in different ways in different cell designs, but the basic premise is the same. Electrons move from the anode to the cathode, and the ions in the electrolyte move to keep the anode and cathode charged neutral. As a result, the electrons keep flowing. This mechanism is extremely powerful, as for long periods of time, we can hold a roughly fixed potential difference across our conducting wire, which electrons can flow across at a constant rate. Now, of course, there are limitations to this. There are only so many ions in the electrolyte, and only so many electrons in the electrodes. Electrochemical cells could stop working for a few reasons. Perhaps it's the electrolyte that's run out, or a fault with one of the electrodes. But either way, we just aren't able to maintain the potential difference forever. This is completely logical, as otherwise our cell would have infinite energy. The first ever electrochemical cell was built by Alessandro Volta in the year 1800. It consisted of copper and zinc coins, separated by cloth soaked in seawater. As we've established, copper is an element that accepts electrons, making it the cathode, while zinc is an element that easily gives up electrons, making it the anode. The cloth soaked in seawater is our electrolyte, containing dissolved salt and water. The dissolved salt consists of free-moving positive and negative ions, which move to prevent charge buildup in the copper and zinc coins. It's an ingenious invention, and for each cell consisting of one zinc coin, one copper coin, and one electrolyte, we get an approximately constant potential difference. If you remember from the last lecture, the total potential due to multiple charged systems is just the sum of the potential due to each system. So, if we stack multiple cells on top of each other, the total potential difference across the whole thing is just the sum of the potential differences across each cell. This is known as a battery, and it consists of several cells stacked together. This was originally built by Alessandro Volta, but I should also mention another Italian called Luigi Galvani. This type of battery design is specifically called a voltaic pile. But before the battery was invented, in the 1780s, Galvani accidentally created a cell out of a dead frog's leg, out of all things. By attaching a zinc and copper coin to it, the leg would experience a small voltage and start twitching. In honor of this, the electrochemical cell was named a galvanic cell. In the present day, there are many different designs for batteries, but the same idea applies to all of them. There are always two electrodes where one material is more able to give up electrons than the other, such that it becomes the anode, and the other material becomes the cathode. These two materials are connected with a wire, so electrons can flow from the anode to the cathode due to the potential difference. To stop charge buildup at the electrodes, we use an electrolyte, consisting of positive and negative ions that can move around to balance the charges. As a result, we can maintain a potential difference across the wire, such that electrons can flow through it at a constant rate. Now, to build a useful electronic device, we simply put things along our wire for the electrons to pass through. This is known as an electrical circuit. We'll decide what to put here later. We can draw electrical circuits in a simple way by drawing lines for wires and various symbols for electrical components. We denote a battery with several small and large lines, where the large lines indicate positive electrodes and the small lines indicate negative electrodes. We can draw on plus and minus signs to help us remember. Now, one big disclaimer here. Do not build this device as is. These batteries might not seem like much, but applying even a small potential difference over nothing but a copper wire is extremely dangerous. This can easily lead to overheating and start fires. We'll explain why this happens in the next lecture, but I'm just putting it out there now in case any of you thought about building one of these yourself. A very useful quantity for us to measure is how quickly charge, carried by electrons, is moving through our circuit. In other words, looking at a point on our circuit and figuring out how much charge flows through here per second. This is called the electric current, and is simply the amount of charge, delta Q, that flows through a point over a period of time, delta T. It is denoted by the symbol I, and is equal to delta Q over delta T. The electric current therefore has the units coulombs per second, although we also have a special unit for it called amps, which is equal to this. The amp is named after André-Marie Ampère, a French physicist who showed that multiple wires with electric currents actually interact with each other. This interaction was then used to measure the amp exactly. Since then, we have defined it in terms of elementary charges E. Don't worry too much about this, as it's way beyond what we will discuss in this lecture series. Anyway, we can more generally write the current in derivative form as dq by dt. We usually don't use this for simple circuits like this one, as the current stays constant here. But in some more advanced situations, the current does vary, so this is the exact definition. Either way, the current is simply the gradient of the charge versus time graph. One nuance to mention with electrical currents is that negative charge is moving. As the current is plus the change in Q over the change in T, and the change in Q is negative, the current actually points in the opposite direction to the movement of electrons. This is sometimes overlooked, but is important to remember. A really cool feature of electric currents is that they are constant anywhere in our circuit, at least when it is designed like this. As electrons repel each other, we can't have regions in our circuits with different currents. If you were to speed up an electron, it would catch up to those in front, and therefore experience a larger repulsion from them. Likewise, if it were slowed down, it would experience a larger repulsion from those behind it. So, no matter where you read it from, the electric current will be the same. We'll see later that it doesn't apply to all circuits, only series circuits. Series circuits are those where the current only flows along one path. There are circuits, known as parallel circuits, where we can send the current along multiple paths, such that the current will be divided along each path. But we'll get to that in a few lectures' time. Now, there is more I want to say about current and circuits, but this lecture is already getting quite long. Let's summarize what we've learnt so far. An electrochemical cell consists of an anode, a cathode, a connecting wire, and an electrolyte. It allows us to apply a constant electric potential across the wire. A battery is simply several cells added in series. The constant potential difference generated by our battery leads to a constant flow of electrons around our circuit. We can define the electric current as the amount of charge delta Q flowing through a point over a period of time delta T. More generally, it can be expressed as dq by dt. It is measured in coulombs per second, or amps. In the next lecture, we'll discuss our system in a little more detail. So far, we've only looked at the current in terms of charge through a point, but we haven't really thought about it in terms of the individual electrons themselves. It turns out that there are some very neat ways of understanding the electric current that relate to the potential and electric field. We also haven't clarified how the current relates to the potential difference. What determines how fast charge moves through our wire? Next time, we'll talk about the microscopic picture of current, electrical resistance, and Ohm's law, which connect all this together.